let's get started. So what if there is a hole at the middle, like a donut, as you can see over here? So in that case, we are not interested in anything over here. The only part that we are interested, the only volume that we are interested is the volume of this side, but not the hole over here. And that is where the washer method comes in, right? So quickly, it has a formula V, which is actually the same, and then equal to pi, and then we have what? Integral of, let's say, a to b, right? Into brackets, r squared minus small r squared dx. And you have to take note that mostly this happens when you are plotting what? Two functions. For example, let's quickly look at something in GeoGebra. When you have two functions like this, right, and you plot it, you can see that I have this, and then I have this as well. So in that case, I am just interested in the volume of this part, right? In the volume of this part, and not the space between this particular axis and that of what? The axis of revolution, right? We are interested in the space between the two curves and then the axis of revolution, and that will be our volume of revolution. So let's quickly look at how the formula also came about. So coming back to our blackboard, we can say that it is the same, or it follows the same format as the Dix method. In this case too, we also approximate it what? As the Dix method. We approximate it as what? The Dix as well. But what we do is that, let me quickly go back to GeoGebra and show you. Let me pick something from view and then get a 3D shape. And as you can see over here, you can see that for this shape, let me turn it off. For this shape, there is a hole at the middle over here. And after this hole, you can see that there's a volume occupied by these two curves. And you can see also here the volume occupied by these two curves after the evolution. And that is the space or the volume that we are interested in, right? So in that case, how can we get it? So you can get this by, first of all, let me quickly do some sketch over here. Let's say I have my y-axis and then my x-axis, and then let's say I have something like this, and then I also have maybe something like this, and then I've been able to revolve it around the x-axis, something like that. Remember, it's not drawn to scale, but it should be somehow symmetrical about the axis of what? Evolution. So in that case, this is the figure that I'll have. So I'll be able to approximate the what? The radius. And how do I do that? Because remember that we also use the same area of the circle, which is what? Pi r squared. So in that case, we consider the outer function as what? The bigger, let's say, curve, right? Let's say it has a radius of capital R, and then the inner curve, we have a radius of what? Small r. So in that case, we can say that the area of the outer curve is going to be area 1 equal to what? Pi capital R squared, right? And it will have the radius from the axis of rotation to that of what? The function, and we can calculate what? Its corresponding y value, right, over there. So now, when you look at the inner function as well, we can calculate the radius from the axis of rotation to that of what? The function, and we'll be able to what? Calculate its corresponding what? Y value at each point, and that will give us the distance from the axis of rotation to that of the function, which is what? Our radius, as I explained earlier on. So for the outer function, the area is equal to pi r squared. For the inner function, let's say a2, we also have an area of what? Pi small r squared. So in that case, if I only want the area of this small space, what do? I have to subtract the area of the smaller or the inner function. That is, this is the whole area of the function, right? This is the whole area, but the inner function only occupies this area, and then the outer function only occupies this area, which is a combination of the inner area and that of the extra outer areas, right? So in that case, if I subtract the outer the inner area function from that of the outer area, I'll get what? This area, right? The area which is occupied, or area under the true curve, right? So in that case, the total area is equal to area 1 minus what? Area 2. And in that case, we are going to get, let me put it here, area, which is the total, equal to area 1 is pi r squared minus the area 2 is also what? Pi small r squared. In that case, my total area is going to be, pi is common, so we bring it out, and then we get r squared minus what? Small r squared. So when you have such questions, right, the only thing that you have to do is to be able to what? Find the radius of the outer function and that of the inner function, right? And that's what we explained earlier, how to find the radius when you are being given, or when you draw the figure, how you can find the radius. And if you are able to find the area radius, just subtract the smaller radius from what? The bigger radius, and you'll be able to find the total what? Area right under the two curves, right? So let's quickly also look at something over here, which is really interesting. After finding the area, which is the area occupied by what? The two curves. These are the space that we are interested in. What next? The next is to integrate the area, right? So if I decide to integrate the area, I'm going to do integration from the limit a to b of pi into brackets r squared minus small r squared, and then dx, right? And in this case, that gives us what? The volume of this particular figure. That's the volume of revolution. Is that okay? So that is how you can use what? The Walsh method to kind of what? Find the volume of revolution when you are being given such figures. And mostly the radius are expressions, because the function is in terms of a particular variable. And in that case, when you substitute them inside here, it becomes what? An expression. And therefore you can integrate over that expression, and you'll be able to find the volume by what? Putting in the limits from, let's say, a to b. So in general, what I will say about the volume of evolution for either the x-axis or the y-axis, or above on a line, is that for above the x-axis, we can say that our volume of evolution v can be equal to the integral over the limit a to b of the area, and the area should be a function of x, or it can be a function of any other variable with respect to that variable, what? X, right? For the y-axis, if you are rotating the curve about the y-axis, what you can do is that the volume can be equal to the integral over the limit a to b of the function, because we are integrating with respect to, or we are revolving it around the y-axis, we need to let the function, or express the function in terms of the y. In that case, the area will be in terms of y variable, that is a of y, and then with respect to y. So by looking at the Walsh method, if we have two functions and we are being asked to find the volume of revolution between of the two functions, right? And if we are either revolving around the x-axis or we are revolving around the y-axis, I showed you the exact area or the volume that we need, and in that case we can express that function as the volume to be equal to the integral of the over the limit a to b of, let's say, the bigger area, right? The bigger area, and then let's say the bigger area, let's say a2 minus the smaller area, let's say a1, or with respect to what? Let's say x, if that is if you are revolving it along the x-axis, or if you are revolving it along the y-axis, then that means that you will have to actually change let the function in terms of x y variables, and then you have to integrate it with respect to the x, and also the limits must be changed in terms of what the y axis. And this one too, the limit should not be the same of the x. Sometimes you'll be lucky and you get the limit for the x axis to be same as the limit for the y axis. And those type of functions, when you are solving the questions, you have to find the exact point at which each function, or the function meet each other, and in that case you'll be able to know the limits at which you are supposed to integrate up to. So when we solve a question, I'll let you know how to approach certain functions in terms of finding the volume of evolution of such figures. So my next tutorial will be on solving some examples using the Dix method and that of the Washer method as well, and also how you can find the volume of revolution when you are neither revolving around the x-axis or the y-axis, but maybe you are revolving around a line. It can be x equal to a constant or y equal to a constant. I'll let you know how to do it. It follows the same approach but in a different way. Yes. Thank you for watching, and see you in my next tutorial.